Okay, so now we want to prove of theorem 1.4.5. So this is about the existence of square roots. Okay, first one comment I wanted to make. So we're gonna do this for number 2. So we're gonna find the square root for 2. So number whose squared is equal to 2. But this can actually be done for any real number. I mean, you'll see that there's nothing particular about 2 here. We can pretty much redo the proof for every single number in R, and we will have shown that every number in R, every positive or non-negative number in R has a square root. Okay, so yeah, so it needs to be a non-negative number. But as long as it's a non-negative number, we can replicate basically the same proof, just changing the number 2 that we're going to be using here for that particular number for which you want to find the square root. Okay, so what is the theorem? Theorem is theorem 1.4.5, and this says that there exists a real number alpha, meaning alpha is in R, okay, so no such, just satisfying alpha squared is equal to 2. Remember, so a number whose square is equal to 2 is the square root 2. I mean, so there's a square root of 2. As I said, I mean, if you look at the proof carefully, there's nothing special about the number 2 here. We can replace it by any given real number. Again, a non-negative real number. So, so set, I mean, this is just going to be basically recalling the definition that we were given before. But we're going to set this set t. We're going to set this set t. So t to be the real numbers, as it said, such that the square is less than 2. Again, I mean, we've defined this set in the past, and what is important about it was we've already shown this, and so the set T, what important property does it have? The set T is bounded above and below, but we don't actually need that. It's bounded above. We've already shown that. For instance, 2 is an upper bound for this set. Why? Well, you can go and review the material from previous weeks to find out why, if you don't remember. But the set is bounded above. And since it's a bounded set, I mean the set bounded from above in the real number, subset of the real numbers that is bounded above, then we must have that there is a supremum. Let's call it alpha. I mean, there's no surprise here. I mean, we're using the same notation for alpha for the square root we want to find. I mean, this is intentional because the supremum is going to be our square root. Okay, so let's call it alpha, and what we want to show, so we want to show alpha squared is equal to 2. Like I said, we have three possibilities. There are three possibilities. First one, alpha squared is less than 2. Second one, alpha squared is equal to 2. Or third one is alpha squared is greater than 2. Remember that the real numbers as we constructed them. Um, so the set is an ordered field, which extends the rational numbers. I mean, preserves the order of the rational numbers and all the operations, rational numbers. But in particular, we have that there are only three possibilities with respect to whether alpha squared is a smaller number or equal or greater number than 2. So there's these three possibilities with respect to how big alpha can be. It's either smaller than number 2, the number 2, equal or greater. And what we'll show is that this implies this would imply for alpha, this imply alpha is not an upper bound. Well, the last one shows that implies alpha is not the least upper bound. So such an alpha such that alpha squared is greater than 2 is always so that alpha is always an upper bound for the set T, but if it's greater than 2, it cannot be the least upper bound. So this is, I mean, so we're only left with the possibility here in the middle, which is that alpha squared must be then equal to 2. And so that's how we prove this fact, by showing that the first and third possibilities do not hold. Okay. So we'll start with the first thing. So let's assume that alpha squared is less than 2. Yeah, so we want to find a number in T that is larger than that alpha. If you send this, we have a number in t that is larger than alpha, then that means that alpha cannot possibly be an upper bound, right? And this is part of a computation we already performed, so that's why I'm giving you time to think about it. To remember what we try to do? How did we try to make how do we try to find a slightly bigger number such that the square would be still less than 2, a number that is bigger than alpha? Try to see if you can recall. Try to think of the simplest form in which you can try to find such a number. Yes, so the simplest candidate here would be a number of the form alpha plus 1 over n. So something really small. So here n is not known. We're going to try to find such a number n such that this is still less than 2. So the question here is, can we find such an n? And if you remember, I mentioned at the time when we covered this in one of the lectures that the existence of such an n would follow from what? If you said the Archimedean property, you're right. Let's see how. Here I just expanded alpha plus 1 over n squared. This is the first number squared plus the second number squared, and 2 times alpha times 1 over n. Okay, so we have all the 2 terms in the binomial. Okay, so we can definitely say if n is large enough, so if n is greater than 1, this is certainly the case. Let's see why. Because 1 over n squared will be greater or smaller than 1 over n. 1 over n squared being bigger than 1 over n, we multiply by n on both sides of this inequality. Remember that n is positive, so we don't screw up the order of the inequality. Less than 1 is less than, we have the 1 over n squared is less than 1 over n, so we have that 1 over n is less than 1, which is then equivalent if we multiply by n again. We're going to multiply by n squared immediately, but I just wanted to show you that this is a very small number. If n is bigger than 1, much bigger than 1, and this is exactly what we're assuming here. Okay. Okay, so we can now put these two fractions together, and we can write alpha plus 1 over n squared as alpha squared plus 2 alpha plus 1 over n. And what do we want to make sure now? We want to make sure that alpha plus 1 over n squared is less than 2. So we want that this is less than 2. So how do we accomplish this? So let's think for a minute. So if we want to force this to be true, so what we want, so this is equivalent, this is equivalent to saying that alpha squared is less than 2 minus 2 alpha plus 1 over n, right? This is exactly what we want. We want to make sure that n is big enough so that this inequality is true. So this is how we find the n. So actually, sorry, so yeah, then I would like to move the 2. So let's make things simpler here. So in fact, I'm just going to move the alpha squared onto the other side. This is going to make things simpler. So this is equivalent if we just move the alpha squared to the other side. Because what do we want to isolate here? We're interested in finding a condition for n. Alpha here is given, and 2 and 1 are given here. So we want to isolate that, but instead of moving things twice, 2 times, 2 different occasions, we want to move things only once. So 2 minus alpha squared. Okay, so 2 alpha plus 1 is less than 2, 2 minus alpha squared. Alpha being the upper bound has to be positive, so we can divide or multiply by 1 over 2 alpha plus 1, or what's the same, divide by 2 alpha plus 1, both sides. Remember the alpha is the supremum, so it's a positive number, because that set t contains 1, for instance. So this is equivalent to asking that 1 over n, asking asking us to find a number n such that 1 over n is smaller than this number on the right. How do we know that there's a number n such that this is true? Well, if we happen to know that this is a positive number, then let's go back to the Archimedean property, and we'll see that the second part actually tells us that given any positive number y, we can find an n such that 1 over n is less than y. So what is this positive number? It's 2 minus alpha squared over 2 alpha plus 1. Why is that a positive number? Well, alpha, we're assuming that alpha squared is less than 2. Remember, this is by assumption. We're assuming that alpha squared is smaller than 2. And 2 alpha plus 1 is positive, so that this fraction here is positive, so there is such an n. Okay, so the Archimedean property guarantees that there is such an n, such that 1 over n is less than this number here. So this is what we want, but we already know that, we transform everything into something we knew was true, but we cannot proceed like this, so we actually have to go back to the beginning. And now that we know that there's a number such that 1 over n is smaller than this, or 1 over n is such that the number, there's an n large enough such that 1 over n is smaller than this number here, then we need to check then that for that choice of n, alpha plus 1 over n squared will be smaller than 2. So let's check that. Such an n. So going back to this computation here, we see that this is, remember we already have this. This is equal to alpha squared plus 2 alpha plus 1 over n. What had last inequality. We're already replacing 1 over n squared by 1 over n. We're bounding 1 over n squared by 1 over n from above. And so now we can proceed and say, well, then this quantity here will be less than 2 because since this is equal to alpha squared to alpha plus 1 over n, this is going to be less than alpha squared plus 2 alpha plus 1 is positive, remember? And 1 over n is smaller than what? Then 2 minus alpha squared over 2 alpha plus 1. We chose an n such that we chose an n such that 1 over n is smaller than 2 minus alpha squared over 2 alpha plus 1. And then we multiply by 2 alpha plus 1, which is what we have in the numerator here. So this 2 alpha plus 1, the top and the bottom cancel out, give us 1. This is equal to alpha squared plus 2 minus alpha squared, and we can cancel these alpha squares and we get 2. So there's an n in n such that alpha plus 1 over n squared is less than 2. But this means that alpha plus 1 over n belongs to the set T. This is a set of all real numbers whose squares are less than 2. And so alpha plus 1 over n certainly satisfies that. Alpha plus 1 over n squared is less than 2. At the same time, is greater than alpha. And this then alpha is not an upper bound. Right? Okay, so then if we have an alpha such that alpha squared is less than 2, what we've shown is that alpha cannot be an upper bound for the set T. Okay, but now what happens on the other side? Now if alpha squared is greater than 2, then as you can probably guess, we can proceed similarly and find some n in n such that what? Alpha minus now 1 over n squared is still greater than 2. This shows that alpha is not the least upper bound, because we can find a smaller number squared, a smaller number than alpha. If alpha squared is greater than 2, we can find a number smaller than that alpha, such that its square will still be greater than 2. And all numbers whose squares are strictly greater than 2, so the numbers, say beta, such that beta square is greater than 2, satisfy that they are upper bounds for the set T. This is something we shown a couple of weeks ago. And so this would rule out the possibilities of putting everything together. This would show that alpha squared then must be equal to 2. So the details, first of all. So the rest of details. So can be found, well, .4c. So better way to put it is are requested from you in exercise 1.4.7. Okay, so this is something that you're probably going to be asked to do for the homework. It's a good exercise. And unlike the construction of the real numbers, this is the kind of things that these are things that we will be requiring from you. Okay? And to finish everything now, we just concluded something I mentioned at the beginning. We can adapt this proof by substituting, by thinking of this number here be an x. Instead of 2, we put an x here and everywhere in the proof. And what we can show is that any number x that is greater than or equal to 0 will have a square root. So you just define the set T here to be the set of real numbers such that T squared is less than that x. And then you'll find, well, if x is certainly greater than 0, you'll be able to, this set will be non-empty, and so we'll have a least upper bound. And if it's equal to 0, then of course 0 satisfies that 0 squared is equal to 0. But if the number x is positive, then you define a corresponding T, the set of for the set of real numbers such that T squared is less than that x. Remember that we're taking x to be x a positive number, and then we can proceed in the same way to show that the supremum of that set must satisfy that its square is equal to the number x. And so that's all we have to say about the construction of square roots. Now we'll have to deal with a few problems a few exercises, and that's it for now. Next thing we'll be discussing is the cardinality. So we'll see how much bigger R is than Q. This is not really something that we'll be using a whole lot of. So I mean, we're just gonna go through it very quickly and just use the most important facts in the future, but the arguments and such are not really that important. The arguments and the content of, for the most part, the content of section 1.5 is not going to be that relevant uh, from thereafter. I mean, from now on, we're just going to be doing analysis. So, and for that, I mean, the cardinality, issue of cardinality is not going to be that important. Only perhaps if we discuss perfect sets and things like that. But even then, it's really not that important. So we're not gonna be dwelling too much on it. Okay. So then we'll see each other then on Thursday, and then next week we'll continue with this with cardinality, but hopefully we'll move quick enough so we can continue doing analysis. Like this is what we started doing this week.